to name them, yes? We talked about naming amines. Today, we're going to do some stuff with them. So we'll go ahead and get started. So let's talk about amines as bases. We know that, a standard base that we use is ammonia, right? NH3 is a weak base. Pretty standard. And if you remember kind of its conjugate acid has a pKa of around 10 to 11 or so, thereabouts. So this is a pretty weak acid coming from a weak base. That's pretty standard, right? From what we remember about acid-base equilibria. And it turns out we can kind of tweak this. So we're going to see that many kind of just alkylamines also behave similarly. So we're going to see that things like, no matter kind of what crazy stuff we put on them, if we take triethylamine, make triethylammonium, that has also a pKa of roughly about like 10 to 11, somewhere in there. So all these kind of alkyl substituents don't really change our pKa. So put whatever alkyl groups on, you probably won't change the basicity of it. However, once we throw aromatics in, the anilinium ion has a pKa of roughly 4 to 5 or so, somewhere around there. And the reason for this is because we have resonance going on with this. So the electron density that usually the nitrogen will use to grab a proton whatever our base is, or our acid is, whatever electron density is on that nitrogen, that's what's being used to grab the proton, right? So the acidity depends on electron density on the nitrogen. So, I'm sorry, basicity. Basicity depends on that, right? So however much electron density we have there, then it can go ahead and act as a base, grab a proton off something else, and poof, you've got your anilinium now. The reason that a regular old alkylamine, notice its pKa is quite higher, which means this is a stronger acid, right? The anilinium is a stronger acid than the triethylammonium. Is a stronger acid, which means that it came from a weaker base, right? The lower your pKa is, the stronger your acid is. The stronger your acid is, the weaker your base is. So as a result, because the anilinium is a stronger acid than the triethylammonium, we're going to see that the aniline is a much weaker base, 10 to the 5th power weaker of a base. So the reason for that is resonance. The aniline will resonate its electrons into the benzene, thereby reducing the density of electrons on the nitrogen itself. So because of resonance, it goes into the benzene. right? So as it resonates around in there, the electron density is moved away from nitrogen. Interestingly, we have another one. Not right. 2 protons. There we go. The pK of this thing is between 0 and 1. Very, very strongly acidic. Which means that perol, which is what this comes from, is a terrible base. On the order of chloride or something like that. Why is perol such a terrible base? I mean, it's still got some resonance, right? I mean, technically it's resonating, but why is this one 4 to 5? Why is perol 0 to 1? Why is perol so much weaker of a base? And why is the perolium so much stronger of an acid? What's special about this? Eric, you're real quiet. Say again. Or whoever that was.
I was going to say induction, but
Nope, not quite. So why is... What's that? Yes, yes, yes. This thing is aromatic. This thing is non-aromatic. So that's the reason, absolutely. So when perol grabs, this lone pair participates in the aromaticity, right? Because it's on a heteroatom, meaning it can come in and join in and make a happy circle of pi electrons to make this thing aromatic. However, as soon as you use that lone pair to grab a proton, poof, now you can no longer do that. So it's no longer aromatic. So that's the reason for this. So this one is particularly low because grabbing a proton ruins the aromaticity of the molecule. Interestingly, though, when the lone pair does not participate, here, so pyridine or pyridinium has a pKa of also around 4 to 5. Same as a plain old aniline. The reason is because the lone pair on pyridine does not participate in aromaticity. In perol, it does. In pyridine itself, the lone pair does not participate. This thing will be aromatic in either case. So the pyridinium and the pyridine are both aromatic because that lone pair doesn't do anything. It's not participating. If it did participate, then you'd have an 8 pi electron system and bad things, anti-aromatic, but it can't anyway because of geometry, so we're good. So pyridine, although it is aromatic, the lone pair doesn't participate in the aromaticity, so it can go ahead and act as a normal aromatic amine. So like aniline. But perol, because the lone pairs are participating in the aromaticity, if you react those away, you end up with something far less stable. So there we have it. Alrighty. A couple more things about these. Let's look at a couple more examples. Let's make one of these protonated. So couple of other things. Depending on what else is around, we're going to see the pKa of this one is about 1. pKa of this one's about 6 to 7. So on the left there, having an amine as a substituent has increased our pKa, making us a slightly better base because we are a weaker acid now. The reason is because both of these, or rather this one donates it donates electron density into the ring. And so if you look at what the base used to be, it used to be amine on both sides. Remember that we want electron density in there so that we can have that act as a base. So it has enough electron density to go grab a proton. And so, as a result, having an electron donating group will bump up your basicity, thereby lowering your acidity. Nitro group, on the other hand, withdraws it. We already saw that resonance just on plain old aniline made it much weaker of a base. But now putting on an electron withdrawing group, now we're going to have a far, far, far weaker base, a much stronger acid as a result. So those are kind of substituent effects that you can look at with some of these things. And so as a result, we can have amines that have a varying range of basicity. So alkylamines, roughly pKa of 10 when they're protonated. So like triethylamine. Ta-da! Your aniline, pKa of about 5, give or take. And then we've got substituents we can put on. Perola is kind of a special case because you need that lone pair to be aromatic, so it's not going to be basic at all. But some of these other ones, like pyridine, go right ahead, use your as a base. And then, of course, we have substituent effects. So some sort of kind of induction things happening here, but it's more about the resonance, so where we can push the resonance to. All right, so let's see here. Let's do a couple of comparisons. Just FYI, I'm going to write it out, but remember low pKa, strong acid, base. Say pKa does it. I'll say stronger and weaker because we don't want to say these are strong acids necessarily, except maybe the Perol one. All right, so let's do some comparisons. How about we look at this? Which of these is going to be the stronger base? And why? No number is required. Of course, we are looking at the nitrogen. The oxygen is not going to be our base. So what do we think? 50-50 chance, right? Go ahead. First one, stronger base, why? It is not a benzene, but you're absolutely right, though, in that it is still technically donating electron density a little bit. You could resonate it. Well, no, you can't. You can't resonate it, but consider what you can do with the other one. This one, poof, you can indeed resonate. So even though, yes, it's not a benzene, if that was a benzene, yeah, give and take, or obviously you could resonate in and poof, now you've got extra electron density on the nitrogen. Right. But this one, you can resonate to make to give to get rid of your lone pair on nitrogen. And that would make it far weaker, right? Can't even act as a base in this resonance form. And indeed, because there's this pesky hydrogen here, we cannot resonate in either direction for this one. So what's going to happen is this will actually probably stabilize your conjugate acid a little bit because it'll inductively withdraw some electron density away from the positive nitrogen. That might help things out. But big thing here is the resonance for the second one. Once it resonates, it can't act as a base anymore because now there's no lone pair on the nitrogen. So as a result, this one will be the stronger base. Because of that resonance. So no lone pair can no longer act as a base. So part of the time it's going to spend in that resonance form without any lone pair. So no bases, no base is going to, it can't act as a base sometimes. All right. Any questions so far on this acid-base stuff? All right. Just to put this out there, though we'll cover this more later. In living organisms, specifically humans, physiological pH, amines are protonated if they're alkylamines. And so we're going to see that amino acids, like, I don't know, what do we have here? Valine. Oops, this should definitely be protonated. We're going to see, or deprotonated, that amino acids, like this alkylamine, this valine, which I don't remember if it's a wedge or dash. I'm going to go ahead and say a wedge, but I don't remember. So just keep in mind, in biological systems, these will be protonated already. So this is important for pharmaceutical design, that when you're looking at various drugs, you have to consider what form they need to be given as. So this is valine. This is either I think this is L-valine. It could be D-valine, but who knows? One of your amino acids. Let's see. Let's look at some. Let's look at some drugs. Zoloft is one of them. We'll draw you some Zoloft. Actually, the CL's on the other side. You don't need to know the structure of Zoloft, but suffice it to say, it's typically given as, this would be Zoloft. Typically, you'll see it as something maybe with a hydrochloride on it, so you might see it as, ta-da! So, because in the body, it's going to go ahead and grab that proton anyway. So, oftentimes it's helpful to just already give it with it. So you'll see a lot of drugs will say hydrochloride on them, and that means that you've probably got an amine in there. And so the hydrochloride is there for a couple of reasons. Generally, it makes it an easier compound to work with because organic compounds, as you know, can be kind of what's the word? They're not crystalline like salts would be, and so that they can be kind of like difficult to work with. They can be pasty or kind of goopy and tough to work with. But if you make them into hydrochloride salts, they are a bit more crystalline because we've got ions now present in there, and so they can organize differently. And as a result, you can get kind of easier things to work with. So, fun stuff. All right, so amines pretty common. Some biological warfare agents are also amines, but we won't worry about that. All right, let's talk about how to make them. All right, how to make amines. Do we know any ways so far? Kind of vaguely. We know one. We know how to make aromatic amines. Right, we can do a reductive, or we can reduce a nitro group to an amine. Something we've learned. But we don't quite know many others, do we? I'll give you a couple easy ones. Ones that we're not going to worry about the mechanisms so far. If you have an amide, reduce the heck out of it. Oops. If you reduce the heck out of an amide, if you do that, you'll get an amine. Ta-da! So reduce it like crazy. Throw in your lithium aluminum hydride. You'll probably have to protonate something later, and then poof, now you have an amine. So you cannot do your Clemenson or Wolff-Kishner or what was the other one? The sulfur thing. You can't use those with amides. Those are only for aldehydes, ketones. Amides are far less electrophilic than the aldehydes and ketones are, so you're not going to be able to do those sorts of removals of carbonyls. However, plain old lithium aluminum hydride will do the trick here for us. And we'll see the same is with a nitrile. If we go ahead and throw out a ton of lithium aluminum hydride, we get an amine. So both of these, you can reduce these functional groups and you can get your amines out. So don't worry about mechanisms for these. We'll study these more later on, but I want to give you some synthetic toolkits right away. So you have some ways of making amines that are hopefully pretty easy to see. So these will work. Note that if you're going to make a nitrile, nitriles are easy to make, right? You take your, say, bromine thing, and let's not use acetone. Let's use acetonitrile. Why not? Plain old SN2 reaction. Poof. Now we have a nitrile. Just note that nitriles give you one extra carbon. So if you're going to make those, why am I writing it that way? Note that we have now a fourth carbon in this molecule. And if we want to reduce this, we still have one more directly on. So just be aware of that. If you're going to go the nitrile route, that you will typically end up with, not typically, you'll always end up with one extra carbon. So just be aware of that. So if you're choosing this as a synthesis, make sure that you choose appropriately so that you can account for that extra carbon. So, we'll learn how to make amides later on, but if you have an amide, you can reduce it and poof, you have an amine. All right. And the amide one will not give you an extra carbon. So, hooray. Alrighty, let's take a look at some why we can't just do this directly. If we just put this with ammonia, unfortunately, we're not going to end up with a regular amine. We're going to end up with some craziness. Yikes. We see that, unfortunately, if we try and alkylate ammonia, we're going to end up with a quaternary amine, ammonium. Quaternary ammonium salts, right? We're going to see that by the time we put the first one on, this is now more reactive, just like with Friedel-Crafts alkylation. This is the same problem here. So if we just try to alkylate directly, we're going to end up just polyalkylating the crap out of this. If we put just a plain old one equivalent, we're going to end up with a whole bunch of products. We're going to have some ammonia. We're going to have some ammonias with 4 of these things on them, with 3, 2, and 1 thing. We're going to get all of these. But the reason is the first one you put on makes it more reactive because you're donating electron density, right? Remember that alkyl groups are weakly electron donating. So they donate electron density to the nitrogen. Therefore, it can act more as a nucleophile. And the more you do that, the more reactive it gets. And so it just keeps on going until it has 4 of them. All right, and so it just keeps on happening. All right, so this is something called exhaustive alkylation then. You keep reacting the same molecule until it cannot react anymore, and now you have 4 isopropyl groups on your nitrogen, and there are no more alkyl groups you can put on. Right? You have 4 already. There's no way you can add a 5th one, so you're done. You have exhausted your poor ammonia. Typically, though, this will be done on purpose because we can't control it. And we're going to see later on what we can do with these. When we talk about the Hoffman elimination, it uses this idea of exhaustive alkylation. Because we're going to see that ammonia, or rather the amide ion, is a terrible leaving group. But this thing, this trimethyl ammonium, I guess it's a quaternary ammonium salt, right? is a great leaving group. It's positively charged, it's ready to go. Throw in something to eliminate it, and poof, you'll make your alkene later on. We'll look at that. So, but that's the reason. So, ammonia by itself, terrible leaving group. Throw it with a ton of methyl iodide. Now we have a fantastic leaving group. All right, we got thrown all these methyls on there. Now we have a positively charged nitrogen. So it's ready to leave. So we can take advantage of this fact. So, but we can't alkylate them directly, unless our purpose is to get them fully four alkylated groups on there. All right. So this does not make an amine though. So you put ammonia with this alkyl halide, you do not make an amine, you make a quaternary ammonium. So if we're looking at making amines, this won't work. So let's look at a couple of other ways. If we do an SN2 reaction with an azide, we can go ahead and do a couple of things here. We have two options. Hydrogenate it, or do the same thing as before, reduce the crap out of it. We can make an amine. By SN2, we can make a primary amine this way. Works fine. You can make a secondary amine. Tertiary amine, probably not. Or rather, because this is SN2, I'm not talking about the amines, talking about the carbons that it's on. Primary carbons, secondary carbons, great for azide synthesis. You can make your amines this way. Not so great if you have a tertiary alkyl halide, because remember, SN2s don't really work on those. So typically you'll need this to be primary or secondary for using the azide synthesis. So plain old sodium azide with a polar aprotic solvent like acetonitrile, and then we can go ahead and reduce, and now we'll get that. Shall we take a look at the mechanism? I think we should. I'm going to just use a simple old bromide. So this is the azide right here. It has got the three nitrogens, N3 minus, one positive, two negatives, overall means -1. Here we go. It is a nucleophile. Goes in, kicks out your bromine. This is technically SP, so I better do my geometry correctly. All right, so we've got that. All right, next step. Let's go ahead and use our lithium aluminum hydride. We know that the hydride is going to be nucleophilic, so it's going to go ahead and attack our nitrogen, moving electrons over to the positively charged one. As a result, we are left with the following molecule. And now what happens? Our nitrogen, just like with the, I don't know, what's this did we do with that had this happen? We lose our ammonia. Oh, it was the Wolf Kushner, that's right. We lose nitrogen gas. We end up with a negative amide, I'm sorry, this time. And then here is our best friend, the water that's hanging around in step 2. Goes ahead and protonates itself. And so we end up making our amine. So step 1, I can make this work. Azide attacks, SN2 style. This places your alkyl halide or whatever tosylate, whatever random leaving group you happen to have. It's now on there. One of the hydrides from the lithium aluminum hydride complex attacks the nitrogen, pushes electrons towards the positive one. The azide then collapses on itself, getting rid of 2 of those nitrogens as nitrogen gas, leaving us with an amide, which then goes and protonates itself, and we're left with now our amine. And notice this amine is on the same carbon. If we tried to use the cyanide instead, we would end up with 1 more carbon. So the azide synthesis will give us our amine right where our leaving group was. So this is great for making primary amines at primary or secondary substrates. Say on instead, I think chromatically that's a little better. So it's going to go ahead and attack a primary or secondary substrate, and it'll make a primary amine. So because your azide does not have any carbons on it, it's always going to be a primary amine. Remember that amines, the primary means a different thing than it does for something else. Because remember, this is still a primary amine on a secondary carbon. This top one is a primary amine on a primary carbon. This is a primary amine on a secondary carbon. So remember, primary amines mean there's only 1 carbon on them. Primary carbons means there's 1 carbon on the carbon. So primary amines can be on secondary carbons, they can be on tertiary carbons. You can't make that particular one with this synthesis, but that's the idea. So just keep in mind that primary amines and primary carbons aren't related necessarily. So just keep those in mind. All right, cool. Any questions on azides? All right. Another one, gabriel synthesis. This one uses, I remember I accidentally gave this structure to you earlier as NBS because I had accidentally put the aromatic on there. NBS, of course, just has the kind of diketone, diamide thing, just the right half of that molecule, and you put a bromine on NBS, poof. This one is potassium dialamide. This will be our nitrogen source for the gabriel synthesis. And so it works very nicely as well. However, it is not very green because we end up Did you talk about green chemistry in 102? Probably not. I don't think it's on Glendale's curriculum. But one thing is atom economy, is that all the atoms that you're putting on should still end up in your final structure. This one, we're only putting that nitrogen in our structure. All those other atoms just go in the trash. So it's a very ineconomic way of making amines. The azide one is much more economic in terms of atoms. All right, here we go. Here's our lovely, lovely bromide. This also proceeds in an SN2 fashion. All right, and then we've got, so we've now got our, amines stuck on this thing. And in order to release it, we just have to give it our good friend hydrazine. And yes, Eric, that is the correct number of hydrogens on there. If we do that, oh, get out of here. If we do that, we end up displacing our amine. We'll end up kind of substituting that in, the hydrazine in, and we'll end up with, we'll end up with our desired product. So this is waste. I bet this is what we wanted. So all of this work, it's pretty simple, right? You just use this phthalimide. It attacks your alkyl halide SN2 style. So just like before, you're only going to be able to do this on primary or secondary substrates. And you're going to make a primary amine out of this. There's its dots there. Previously, you could do an acid wash. You'd end up with 2 carboxylic acids, but it's kind of crappy. So using hydrazine as your kind of like releasing agent is more and more common. So it's a good thing. Alrighty. Shall we make some methamphetamine then? I think we should. This is the target molecule. Let's make it. I guess I should duplicate it so we actually have it. Simple enough to make this from the corresponding bromide, right? We now have 2 means of doing this, right? We have a secondary bromide, propylbenzene with, I mean, it's so easy. You've got propylbenzene with a bromide on it. How easy is that to make? It's easy. Now, we can do either the azide synthesis. I don't know why I'm saying one. Azide synthesis or Gabriel synthesis. That's all it would take to go from this, oh my god, 2,2,2-bromopropylbenzene to methamphetamine. This is why Chalmers wouldn't let y'all choose this as your drug for your drug project. Amphetamine. Ta-da! And that's all we have. Though I think you'd probably need some chirality to this, but we don't got to worry about that. So, pretty easy. Use it in your drug synthesis. Go crazy with it. So you can take your potassium phthalimide and do it. Use your Gabriel. So Gabriel would be step 1. Step 2 is the hydrazine. And there you have it, the azide synthesis. excess aluminum hydride. This is the azide synthesis here. Or you can use Gabriel, use your potassium phthalimide and hydrazine, and poof, now you've made your methamphetamine. So if you are ordering these molecules, you'll be put on a watch list, and the FBI will come to your, or not the FBI, the DEA will come to your house and find your meth lab and stop you. So trust me, they're aware of these sorts of things. Pretty easy synthesis, right? So cool.
Professor, theoretically, we have these chemicals in our laboratory.
Do you? The problem is getting the propylbenzene. That's more of the tough one. So and trust me, like even if you just take benzene and you take your propyl or propionyl chloride and try to do field crafts and all that stuff, they're watching you. So just be aware. The hardest part actually is getting that bromine onto that carbon. That's the tough part of this synthesis, especially if you want to do it chirally. It can be pretty tough. So that's the tough part. However, if you get your bromopropylbenzene, it's a fairly easy process to get the methamphetamine out. So there we have it. Yes, of course, you're very welcome. I'm going to jail, aren't I? Oh well. So let's look at some other ways to do it. Let's look at reductive emanation. And this uses what we just learned. Why am I putting 1? Okay, NH3. And we have our amine. All we have to do is treat an amine with hydrogen and we'll make our amine. Easy. This is perhaps the most common way to make amines is reductive emanation. So you make your amine first and then just reduce it using hydrogen and a catalyst of some sort, and you'll end up with this. And the beauty of this is there are actually kind of other reducing agents that are used instead of hydrogen that are cheaper and a little bit easier to use. Because hydrogen gas explosive, right? Platinum pretty expensive. So we have other ways of doing that. The most common, or I don't want to say most common, but one of the best ways to do it is using not NaBH4, but NaBH3CN. So by having a nitrile group on there, stabilizes this a little bit. Stabilizes the negative charge, right, that we're going to have on this poor boron. So the electron withdrawing group, the cyanide there, stabilizes this. And what's very useful about this is this thing will not reduce a ketone. Or an aldehyde. NaBH4 will reduce a ketone or aldehyde, but this thing will not. And so you can just chuck it in along with your other materials. So you can say, aha, I'm going to take my happy ketone. I'm going to go ahead and put my catalyst, my amine, and this cyano thing. And poof, we will make an amine. So Just do it all pretty easy. Good to go. No toxic hydrogen gas. You'd probably want to do these at least kind of have some time in between doing them because you don't want to put the hydrogen plus with the H minus. You're just going to make hydrogen gas. So probably a better idea to keep them a little separate at first. This one you can probably let it go for a bit and then dropwise add in your NABH3CN and that'll get the job done. You might need just a slight excess of it as well. So, but there you have it. That's how you can take a ketone into an amine. So first you make the imine, and then you can reduce it either using hydrogen gas or you can use a more selective reagent like this BH3CN. All right, and the best part is this one you can make all sorts of amines with. You can make primary amines, secondary amines, tertiary amines. BH3CN. Ta-da! So you can make very different kinds of amines here. So using reductive emanation will work nicely, depending on what you have already. So you'll probably have an imine intermediate, but that's okay. Or you'll have an imine or an enamine intermediate. That's just fine. But now you can go ahead and do this as much as you want. And so it works really nicely. It works really nicely. So you can just take the same thing and keep on adding stuff to it. All right, so good stuff. You can make primary, secondary, tertiary amines all this way. From your aldehyde or ketone. Now we know all these ways to make or to deal with aldehydes and ketones. So very useful little bits here. All right. So this kind of opens the door for us. If we want to make Prozac, these drugs have such damn complicated structures. Yeah, I'll draw the whole thing. All right, here's Prozac. Last step of this thing is probably putting on the amine. And we have a couple of options here. With the synthetic tools we've already learned. So you are becoming chemists, slowly but surely, bit by bit. We can use the amine directly. Can't alkylate it normally, though, but let's look at what we can do. We have two options. Why am I trying to draw this again? We're going to see that we have a couple ways of doing this. Let's see, no, too many carbons. We can go ahead and use either of these as precursors to making our product, which I still have copied, I hope. Yes. We have expanded our toolkit. So you can do it either way. You can alkylate an amine by doing reductive emanation. It's kind of a secret. It may not be obvious to you, but if you just chuck some formaldehyde at this, chuck formaldehyde at it with a little bit of acid, cyan and whatever borohydride thing, poof, you'll do it. You'll end up putting one carbon on. So it's exactly the same as, I have to do it vertically. It's the same thing here. So when we're putting this, we could consider it both ways. We can say we're taking dimethylamine and putting a cyclohexane on it. That's what we're doing here. We already have our amine. We're going to go ahead and throw an aldehyde at it to put one more carbon on, formaldehyde in this case. So we can go ahead and alkylate amines this way. And so it's very useful. So what we drew here with the cyclohexanone turning into this cyclohexyl dimethylamine, I could have written it the other way. I could have said, okay, I'm going to start with this, and I'm going to do cyclohexanone, H plus, and NaBH3CN, and I'm going to get this compound up here. Totally is legit, right? So it just, whichever way you want to look at it. Are you starting with the ketone as your like preferred product and then putting the amine on after? It doesn't matter. So we're going to see here that both of these will work. We can start with the amine and then use an aldehyde on it to alkylate our amine. Or we can start with the aldehyde directly and go ahead and put methylamine on here. Methylamine with H plus. NaBH3CN, and poof, we'll have made our Prozac. So we have tools. We have tools. We can either start with the amine and alkylate it, or we can start with the aldehyde and aminate it. So make the imine and then go ahead and reduce. So lots of tools here. So the point of this is that if an amine needs to be alkylated, so let's say we're trying to make this thing. If we want to make this thing, let's make them all the same. Let's maybe say we want isopropyls everywhere. We want a nice super bulky base. If we want this thing, remember we can't just go directly and say, aha. Because remember, if we do that, we're going to end up with 4 of them on there, quaternary style. But what we can do is use acetone, have it condensed with a little bit of H+, and then our reductive amination reducing agent, and we'll end up making our, I guess I should just fix the arrow. And you'll end up getting your product of interest. So if we only wanted to put 2 of them on, we could just use 2 equivalents instead. So this is a much more controlled reaction. And because of the fact that the NaBH3CN doesn't mess with your ketone, you can do this all at once. Throw it all in there. If you're using hydrogen gas, you're going to have to do them step by step. You would have to do 3 individual steps. First, alkylation, or first you'd make the amine, then you'd reduce it, then make the second amine, then reduce it, then make the third amine, then reduce it. So this lets you do it, throw it all in one pot, and poof, we have made our triisopropylamine out. So very, very useful, this reductive emanation business is. Alrighty. Any questions on this? I forgot a positive here, didn't I? All right. Let's talk about acylation. If you treat an amine with an acid chloride, you will get the amide. And we're going to see that in terms of benzene stuff, this is actually pretty useful. Because this is more kind of in reality. If you take aniline and brominate it, you're going to get bromines everywhere. Because this thing is super activated, right? And it's not a bulky group, so you're going to end up brominating everywhere. However, you can kind of moderate this. You just put in acetyl chloride in there. You end up with your amide, which is now a moderate activator. So this was a strong activator. This is a moderate activator. That's going to calm down your benzene a little bit, so that if you go ahead and put your bromine in there, you're only going to get the para one, predominantly. It kind of calms it down. And then you can just hydrolyze it off. If you just do just base or acid wash, you can get back your amine. So remember that there are some things that we can't do with aniline because it's just too damn reactive. Notice that your fetal Crafts isn't going to work here. Also because your amine's just going to go ahead and attack the acid chloride. So can't do a fetal Crafts, but if you make it into this moderate activator, your amine is not going to be nucleophilic anymore, so you can go ahead and now do a fetal Crafts on it. So you can take this and do a fetal Crafts. You can take this and you can nitrate it. It's ways of taming your aniline. Remember, you couldn't nitrate aniline because you end up with black sludge because you end up oxidizing part of it. Not going to happen if you've protected your amine with this group. And so it's a kind of a useful placeholder that you can do whatever you want to do, and it'll protect your molecule from going to crap. So you can now do all your fetal Crafts and nitration all you want, and then you can just wash off your acetyl group, and you'll end up with your amine. So you can protect it. I don't know. Protection? I mean, it's just making an amide, so there's not really a name for it. But in this case, we're using it as a protecting group. So let's see here. Where shall we write this? Right here, perhaps. Amide as a protecting group. So turning your amine into an amide can protect it from, well, it's not really, yeah, I guess you're protecting it from, or you're stopping it from doing other things. So you are, I guess, yeah, that's what a protecting group does. And so you're using it to shield your amine from going crazy and reacting with other things, and you're also taming it down a little bit. So you're going from a strong activator to a moderate activator, and so that'll help calm down your reaction a little bit as well. And so as a result, you don't get tri-bromination, you only get monobromination. Again, you don't even need the catalyst, you don't need the iron or the aluminum, because it's moderately activating. That's good enough to get your bromine on. So, yes. And then it's removed with just acid or base, whichever one you feel like using. So we'll remove it. The amide. This only works, by the way, for aromatic ones. So you can't remove an acyl group with base or acid if it's not aromatic. So just if aromatic, I'll write that here. We see that in order to go from an amide to just get rid of it, it's pretty tough otherwise if it's not aromatic. So aromatic one's easy, just base or acid. Ta-da. Alrighty. Here, I'll make it a little bit bigger. There you go. So with this, once you have this, here, let's do some random Friedel crest. We don't need to do that. We're good. All right, let's talk about a couple more reactions. We have the Hoffman elimination, and then we have some Sandmeyer stuff to talk about. All right, so let's do it. Back to horizontal. A Hoffman elimination. Hoffman elimination allows us to turn our amine into an alkene by using the exhaustive emanation idea. So we can take a handy dandy amine, go crazy with the methyl iodide, an alkylating agent, and then we'll use a nice base like silver oxide. This is pretty common, and we will end up getting the Hoffman product, where that's the less substituted one. Remember, when you're eliminating something, you have two ways to do it. In this case, you could either eliminate and get the more substituted alkene, the Zaitsev product, or you can remove the less substituted side, which is the Hoffman product. And guess what? That's pretty obvious here, that because this is the Hoffman elimination, we're going to get the Hoffman product. So in fact, that's where this name comes from. So the reason for this is because as we polyalkylate this thing, let's look at excess CH3I, we end up just doing plain old SN2s on this thing. We have our excellent leaving group. And so we just need to think about how this is going to work. We're going to see that if we try and do the, I have to do some Newman projections, which is the fun part always, right? We now have this bulky old leaving group, right? Suffice it to say, if we eliminate the others, I'll just do it. Let's look here, and let's look. We'll look at both of these, okay? We're going to look at kind of both carbons. Oh, my eyes are getting uglier and uglier, but we're going to go ahead and look at some Newman projections, and we're going to see why we're going to get the Hofmann product. As drawn, let's see, we have pointing up. Oh, the meth group is up, actually. Wait, what am I looking at? Oh, this is hydrogens, duh. Okay, why did nobody, correct me on that? So we have our amine up there, we've got an ethyl group here, and hydrogen here. So when we eliminate, remember for elimination we need to have anti-periplanar. So when our base comes in, it's going to eliminate and kick this off, right? So we have nice kind of far away, we have no kind of gauche interactions with this. Let's see. We do not have any gauche interactions with this. However, if we look at the other side, okay, so that side, well, let's just say this freaking thing is on a wedge because that's annoying me. And then we have a methyl group down, and then we have what is it, hydrogen. So we see here now we do have gauche interactions. Here happening between the methyl group and the amine. It's a little bit less pronounced with the methyl group. We have like an isopropyl or something, it's even more obvious. But as a result, we have gauche interaction. So if we were to try and eliminate this way, it's less likely to happen. So this is less likely. So when we do eliminate, we're looking at eliminating these two hydrogens, or there's the hydrogen that's down. But when we do eliminate, we're going to see that because of these gauche interactions, this is less likely to happen. Here we have no gauche interactions because we have hydrogens next to our quaternary ammonium, which should have a positive charge. And so as a result, we're going to see that we always get the Hofmann product as a result of this. Because it's so bulky, we're going to get Hofmann out. All right, so it's kind of essentially in E2 type elimination. And your bulky leaving group puts it as Hofmann. So there we go. That's the reason we get the Hofmann product. All right. Exciting. All right, let's look at one more bit. We're going to show this last thing. Yeah, let's do an example. what's the product we're going to get here? We have three potential products, right? When you're determining this, easiest thing to do is look at which one will be your least substituted product. And so let's take a look at what happens if we eliminate those particular hydrogens. If we eliminate the blue one, we end up with this. If we eliminate the green one, we get this. And if we eliminate the purple one, we get this. We see this one is tri-sub. This one is only di-sub, so the winner is the purple one. It's that easy. Just have to consider what beta hydrogens you have and which one will lead you to the less substituted product. In this case, we had two options that gave us tri-sub, and in fact, they gave us the same one, the same molecule. And then we had one that would give us the di-substituted version. So pretty straightforward there. So just choose the least substituted one, the more Hofmann product, and that will be your answer. So they're not too difficult there. Alrighty. Okay, well, whatever. Someone is asking some other questions, we don't care. Okay, so let's look at nitrous acid and amines, yes. We're going to see that nitrous acid and amines opens the door to a lot of interesting things. With secondary amines is a little bit less exciting, but this is what we're looking at here. So nitrous acid, the nitrite ion. Oops. This is a nitrite. Typically what we do is we use sodium nitrite and HCl. This will give us our nitrous acid in situ. But what's kind of useful here is if we have our HCl, we're going to do something similar that we did with the nitric acid and sulfuric acid with the benzene. We end up protonating this dude. And then we do it again. Protonate again. Just like before with the sulfuric acid, we protonate nitric acid, and we got NO2+. We're going to see we're going to get essentially an O+ here, but we'll take a look. Indeed, because what happens is this thing closes down. Apologies on the oxygen. Important thing here, this is called the nitrosonium ion. Which we know is a nice electrophile, just like the nitronium ion was. And we're going to see that this is a very strong electrophile. And so if we take a secondary amine and treat it with this, it'll go ahead and attack it, and we'll make kind of just like as if we were nitrating a benzene, we do the same thing here. But we're instead of putting NO2, we're just putting NO on. And this is a nitrosamine, what it's called. There are a lot of kind of useful things to do with these. These often have very like smoky flavors. Smoky flavors and aromas, so we find them in things like bacon or like smoked fish or whatever, or tobacco. These are very smoky smells and flavors, but they're less interesting chemically speaking. If we do it with a primary amine, we're going to get what's called a diazonium. And I suppose we'll take a look at this next time. These things are ridiculously reactive. If you have just an alkyl one, we see here that we're just ready to lose nitrogen gas, right? And that's a problem because we're going to form a primary carbocation. Or I mean, I guess it depends what the R group is, but we form a carbocation if the nitrogen just leaves and it's ready to leave. So with alkyl ones, these are extremely explosive, but with aromatic ones, they're a little bit more stable. And we're going to see we can do a ton of things with these later on. All right, so we'll look at this reaction next time, and then we'll see all the things we can do with these diazoniums later on. All right, so that's it for today. Don't forget, Monday is our exam. It'll be the same format as last time. So, mechanism, synthesis, fill in the box, naming, that sort of thing. All our fun stuff from before. So, same idea. All right, it'll be the same thing. Take pictures, submit them on Canvas. And I swear to God, if I find things on Chegg, I don't know what I'm going to do. That's a threat. So, please take it as such. Cool. All right. That's it then. I mean, it's really just 2 chapters, right, Audrey? It's aromatic reactions. We have EAS, NAS, elimination addition. This is the aromatic stuff. And then we have aldehyde ketones. Everything. So that's all. That's all it is. So I put some. You have tons of practice for electrophilic and nucleophilic substitutions and elimination addition, though that's less useful. Those are in the extra resources tab. And I just put some stuff on aldehydes, ketones.